I hope everybody had a wonderful weekend. Enjoyed your time, your free time. I don't know if you have free time. I don't have free time. I don't know anybody who has free time. Before we begin, I just want to share my desktop screen really quickly. Let's see. So I put into our site an announcements folder. You can always compress that or collapse that folder if you want to, but there's an announcement folder there because we are coming up on, let me zoom in here. We're coming up on chapter 11, and chapter 11 is the largest chapter in Calc 2. And there are 11 sections in chapter 11, so it's quite a bit of material. And there's a lot of leaning on prerequisite knowledge, specifically your knowledge from pre-calculus of sequences and series. So I made an announcement with some of my videos that are pertinent to chapter 11. So just to let you know, I'd probably watch, if I felt as though I needed to review this, I'd probably watch a little bit of this first video. It just reminds you of what a sequence is and how they work. It's kind of elementary, so you might be able to breeze right through that. Recursively defined sequences, those are somewhat important. Actually, they're the building blocks for the Fibonacci sequence. So if you're interested in that, you can watch that. It's not actually, that one's not technically a requirement. But then partial sums of sequences at sigma notation and using sigma notation, those are very important. Since you're in Calc 2, you probably already are pretty good with that stuff. But just in case, you might want to watch those videos. I think somewhere in there I have a few properties of sigma notation. It might be sigma notation and its properties right there. And then series, those are the ones that are going to be incredibly important. So you do want to make sure you watch at least the first 4 videos here. There's not really technically homework associated with them, but the entire chapter hinges on your knowledge of those. So just giving you a heads up, you'll probably want to watch those within the next couple weeks. Just like to put them up so that you have time to review those rather than the last minute prep. Let's see. Let me share my other screen, hop back here. When's your next test? Well, we have to get through section 7.8. And right now we're in 7.3. We're almost done with it, honestly. So we'll finish out 7.3 today. We might start in a 7.4 today. And then we'll probably finish 7.4 Wednesday, maybe early Friday. And then 7.5 is a review of all the tactics that we have learned thus far. And I spend very little time on that because it's just saying the same thing we've said over and over again about, choosing methods. I have a handout for that, by the way, that a PDF that I'll put on the site that gives you kind of a guideline to what method to choose and when, although everything's breakable. So don't get married to an idea. There are always options. And then we go through 7.7. We don't go through 7.6. We go through 7.7, which is numerical techniques. So that would be like a review of midpoint method, left and right endpoint methods. Then we do trapezoid rule, which is a newer method, and then Simpson's rule. Not me, somebody else, but still a really cool method. And then 7.8 would be improper integrals, which are integrals that go off to infinity. So we still have that to go through. So I'm guessing the exam would probably be 2 weeks roughly from now, maybe 2.5 weeks from now. So yeah. I'm trying to get ahead with you guys and write my lectures and get everything up a little bit sooner so that you guys can have a stronger idea. But you're the only class that I don't have all my videos recorded for. And so that kind of makes it a big question mark about the timing. One thing I am doing, just to let you guys know, is that I am recording, because I tend to have a lot of examples in my lectures. And while that's good for students, it's bad because it slows us down. But I still like to have all those videos, or I'm sorry, all those examples. So what I'm doing is I'm going through my lectures and finding the examples that are kind of, they're examples that if I had time, I would do them. But if I don't have time, I wouldn't do them. And those I'm recording on the side and posting them on our website. So if you have gone back to the, I should have actually shown you this in the, earlier, but if you would go to our My Open Math website and you go down to, let's say, our second unit of material here, and then maybe into 7.2 folder, you'll see that I have the video, the recordings of my lectures on these dates, but I also have 3 extra examples that I just couldn't get to during class time. And they're somewhat optional. If it's a core video, then, or a core example, I would have done it in lecture. Same thing with 7.3, which is what we're currently in. I actually already recorded 2 videos and posted them up because I knew that, well, they weren't really super important for me to cover in class. But one of them is what happens with those absolute values when you're taking the square root of a square, because we're often taking the square root of cosine squared or square root of tangent squared or square root of secant squared. Why aren't those absolute values of those functions? And so I talk about it in this video. And also within that video, I cover a little review of how to do some trig subs. So there's still good videos to watch. I definitely would do it. But anyhow, so that's what I'm going to be doing from this point forward. And you'll see even in 7.4, I already have a video there, which sometimes I do in class, that example, if I feel as though I have the time. Often I don't, but I'd like to derive the concept of our next topic, which is integration by parts, or I'm sorry, partial fraction decomposition, with an introductory example. So anyhow, that's just a heads up that you might want to take a look at the folders and see if there are any videos that I've added recently. Anyhow, all right. So picking up where we left off, let's see. We were in the middle of trig subs, and we had gone through and learned that when we have a sum or a difference of squares, like for example, if we had a difference of squares, right, k minus something being squared, then that we could use a sign substitution, let u or x equal sign, and then we can get the Pythagorean identity from there. And then we had these 2 other highlighted versions here. If you have a sum of squares, you're going to use a tangent substitution. If you have a difference of squares where the unknown is the first thing squared, then you use a secant substitution. And we'll continue with that today, so don't worry if it's been a little bit. And then we went through some examples. I'm just hopping through them to find out where we left off. So let me go ahead and continue forward. Oh, we did quite a few examples, honestly. Okay, so this is where we left off. Example 6. Yeah, that's right. So let's go ahead and take a look at this. Often, sadly, I don't do definite integrals in lecture, and it's not because I don't like them. It's just because timing-wise, it forces an extra little bit of time, a little bit of work there, and I just didn't want to have to worry about that or burn that time. But I think this is a good one to talk about, especially with trig subs. So notice, first thing you're going to do, take a look at this. If there's any algebra you can do first, then do that. So, but there's no algebra I can do here, but I'm just giving you the heads up. If there was algebra that you could do, please do it. But there's no algebra to clean up here. Then you start listing out some tactics. Probably the best idea here is just to say the things, think about the list of tactics from beginning to end that you learned them. You do not know the direct antiderivative here, so I'm not even going to bother writing that down. A U substitution. I made a video about this because the video is called Avoid Constantly Using Trig Subs. It's in the 7.3 section, actually. And it basically says that once you learn how to use trig substitutions, you often knee-jerk into just using trig subs when you could have used a U sub. And U subs are often a lot faster. Just letting you know right here, a U sub is a terrible idea. So it's not going to work for you. Well, it might work, but it doesn't look like it's going to work. I'll put it down as a possible tactic, but to be honest with you, I just don't think it's going to work. So I'm going to write it down as a possible tactic, but I probably wouldn't want to do it, mainly because if you let U equal, let's say, this 36x squared plus 1, its derivative would be 72x. Now, if you look at the integrand, I don't have a 72, but constants don't actually matter. So let's forget about that. But I would steal away a single power of x, and I'd be left with an x cubed. And that's a problem. Being left with an x cubed when u is something in terms of x squared is a little bit of a mess. So I probably would not do that substitution. I'm just looking ahead a little bit as far as how difficult would that u sub be. And then I think about, let's see, we had by parts, right? But by parts is a terrible idea here. Again, I'll write it down and then cross it out. By parts is a terrible idea because it's not a product of functions. So I wouldn't bother with it. Although I've seen some students use by parts in some really interesting ways. To be honest with you, in this case, by parts is just a bad idea. And then we had a section 7.2 called trig integrals. And when I say trig integrals, it's unfortunate how this author labels them. I think he's the only author that does this, but he has trig integrals, and then he has something called trig subs after that section. Trig subs is what we're in right now. Trig integrals is when you have a product of trig functions, like a sine and a cosine, and they have powers on them. So trig integrals, you would only use that method if you had a product of trig functions, which you do not. So I'm going to go ahead and cancel that out. And it's being asked, by parts is only used for products. No, it's not just used for products. It's used for a lot of different situations. By parts, in fact, is how you integrate the natural log. It's how you integrate tangent inverse. It's how you integrate sine inverse and cosine inverse. So it's not just for products. There's always exceptions to these rules. But I'd say 80% of the time it's for products. Let's see. And then now we're into the material that we're in right now, right? Which is trig subs. So I'm going to write that down, trig subs. I think, by the way, the reason why other authors don't have a section dedicated for trig integrals is because they're basically u substitutions. So there's no real need for a section in their textbooks called trig integrals. I think that's interesting. This author just wants to take his time going through it, which I kind of respect. All right, so trig substitutions. This is what I'm going to use here. Notice that denominator is a sum of squares. And if you think about your trig Pythagorean identities, this sort of, it's not exactly, but it sort of looks like a tangent squared of theta plus 1. It's not exactly, but it sort of looks like that. And if I traded it out for a tangent squared of theta plus 1, then that would shrink down or collapse to a secant squared of theta, which is ideal. So this is how you make a trig substitution. This is how you make your mind up for whether you're going to do a trig substitution or not. You're looking at this and saying, well, can I make a trig identity out of it? And the answer here is yes. So the way I'm going to do it, I know I want this 36x squared to be basically a tangent squared. So that's what I'm going to say for my substitution. I'm going to say let 36x squared equal tangent squared of theta. I think in the last lecture, I was saying let 6 or 1/6 x, I'm sorry, I was saying let x equal 1/6 tangent of theta, and then I would square it. But I think this is more natural for students to see it this way. You want that 36x squared to be tangent of theta, which would imply, by the way, that 6x is equal to tangent of theta. And again, just want to reiterate, what I did there is I took the square root of both sides. And normally when you take the square root of both sides, you get a plus or a minus. So normally you would have something like this. However, when you do this substitution, just letting you know, when you do this substitution, you're saying that the tangent inverse, it's supposed to be a tangent, it just didn't quite work out for me. The tangent inverse of 6x is equal to theta. That's what's happening when you make a trig sub, is really you're restricting the angle. You're making a substitution and saying, by the way, I'm going to eventually probably have to solve for theta. So therefore, theta is going to be restricted because all inverse trig functions have restricted angles. And this is restricted to be an angle between pi over 2, or sorry, negative pi over 2, and positive pi over 2. So once I say that, I know, therefore, that if my angles are restricted to be from negative pi over 2 to positive pi over 2, that means that the angles in either quadrant 4 or quadrant 1. And because of that, I know tangent in quadrant 1 is positive, and I know tangent in quadrant 4 is negative. So the positive negative thing that normally would be in front of this is just going to be folded or absorbed into the tangent. The angle itself will tell me whether it's positive or negative. So that's just a little aside. I don't want you to think that I'm just hand waving and saying, oh, the plus and minus, we don't have to worry about it. We technically don't, because it gets folded into the tangent. Anyhow, the next thing I need to do is, since I'm trading out into the world of thetas, I'm going to go ahead and take the differential of both sides. So I get 6 dx is equal to the secant squared of theta, d theta. And finally, and this is kind of important, not just kind of important, it's very important. When you have a definite integral like this guy right here, I highly recommend that you trade everything out into the new world of theta. It's just much easier, I think. Now, often, or I shouldn't say often, but sometimes when you're working on definite integrals, trading out into that new world that you're going into can be challenging. However, in this case, I know it's not going to be, so I'm going to just go ahead and do it. So I'll write this down below, and I'm going to do this here. So when x is equal to 0, that's our lower limit of integration. When x is equal to 0, well, I'm just going to use this equation right here. If x is 0, then 0 should equal the tan of theta. That is, theta has to be 0. And then when x is equal to the upper limit, which is 1/6 in this case, then we have 6 times 1/6 is equal to tangent of theta. That is, tangent of theta is equal to 1. And we know that the angle that you would plug into the tangent to return 1 is pi over 4. Because trig is a strong prereq for this course, I know you guys know all that. It's not just me. Anybody who teaches Calc 2 is a stickler about this. So you have to be up on your trig and your angles. And if you're not, or if you feel shaky with it, which is totally fine for right now, you might want to just draw on each homework you work on your special triangles, and that will at least help you out when you need to find out, well, what angle would I plug into the tangent to get an output of 1? Tangent is opposite over adjacent. So if you said, oh, maybe it's pi over 6, well, opposite over adjacent would be 1 over root 3. That doesn't work. Well, maybe it's pi over 3. Opposite over adjacent is root 3 over 1, so that doesn't work. Maybe it's pi over 4, 1 over 1. Yep, that works. So that's just a heads up. I would probably just get in the habit of writing down those special triangles in the meantime. Anyhow, let's now go ahead and exchange our definite integral here for our modified definite integral, because we're making our substitution. We are now going from theta equals 0 to theta equals pi over 4. Let's see. That x to the 4th upstairs. So let's go ahead, and I'm going to take this right here. I'll divide both sides by 36 and then square it. Let me go off to the left here. So x squared is going to be tan squared theta over 36. And then you would square both sides of that to get what x to the 4th is. So I'll plug that in. So x to the 4th is going to be 1 over 36 squared, whatever that is, and then tangent to the fourth of theta. All right. And let's see what else we got here. The dx. So I've already taken care of the limits here and the x to the fourth. Let's go ahead and take care of the dx. The dx, well, I know that 6 dx is secant squared of theta d theta. So secant squared of theta d theta over 6 is what dx is. So I'll go ahead and pull an over 6 out of this times 6. And then I trade that out for secant squared of theta d theta. Looks pretty terrible, doesn't it? And then downstairs, we traded out a 36x squared for a tan squared. I squared because I need to get x to the fourth, right? Our integrand, our original integrand had x to the fourth. So I squared both sides of this to get that. All right. And let's see, 36x squared is tangent squared. So let's go ahead and trade that out. Tangent squared of theta plus 1. And then we have to 3/2 power. That's the complete trade out. Remember, tangent squared plus 1 is a Pythagorean identity by our choice. So that's going to be secant squared. So it's going to be 1 over 36 is 6 squared. Squaring that 6 to the fourth times 6 is 6 to the fifth. So I'm just doing that. We're going from theta equals 0 to theta equals pi over 4. And I'll rewrite that's a tangent to the fourth secant squared of theta d theta. And then downstairs, we'll have a secant squared theta, and that is to the 3/2. Or in other words, that's going to be the third power of secant. So I'll go ahead and say this is equal to 1 over 6 to the fifth, integral from 0 to pi over 4, secant cubed downstairs. Upstairs, we have the secant squared, and then we have the tangent to the fourth. It does actually clean up a little bit, right? So the secant squareds cancel, and let's go ahead and just leave it like this for right now, and we'll talk. It's a tangent to the fourth of theta over secant of theta, and then d theta. Now we have to make a decision, right? Because you want to integrate this somehow. So I hear a lot of people, they'll say like, well, change everything to sines and cosines, which is actually probably a pretty darn good tactic here. So I'm going to go ahead and see how that looks. If I change everything to sines and cosines, it might be worthwhile. Because right now, imagine the substitutions that you have available. If you let u equal the tangent, well, it needs a secant squared to steal away, and I don't have that. If you let u equal a secant, it needs a secant and a tangent to steal away. And there's a couple issues with that. One being, if I steal away a tangent, I end up with an odd power of tangent. That's a bad idea. So I'm really thinking that maybe just switching it out for sines and cosines, or better yet, you could technically trade tangent out for a secant squared minus 1. You could do that as well. So I'm going to try both of those, or I'll try one, and if it doesn't work out, I'll switch gears. So you can hear the way I've said that even when I go through this stuff, I tend to say, well, I have a couple tactics I'm considering. And if one doesn't work, I'll switch gears and go to a different tactic. That's how you're going to be too. You're going to start these problems, and you have to go in with a couple tactics so that you can change gears at the last minute if something's not working out for you. For right now, I'm going to change everything to sines and cosines. So tangent is sine to the fourth. Sorry, tangent to the fourth is sine to the fourth over cosine to the fourth. And secant is 1 over cosine, so that would be like this. And then you'd have this d theta. Now, here's the problem that I could easily see with this. While the cosines do cancel, just writing that out, we have a sine to the fourth over a cosine cubed, theta d theta. The cosines cancel beautifully, but now you're stuck with needing to make a u substitution. And that is not really going to happen. If you let u equal, for example, the cosine, let's just pretend. If u equals cosine of theta, in fact, let me just show you my shorthand. If u equals cosine, then du would equal the negative sine. And so your integral would have u to the third upstairs. You'd have a negative pop out front. Nobody cares about constants when you're thinking about things here. But you'd steal off a power of the sine. And by the way, that would be a d theta there. You'd steal off the power of sine and d theta, and you'd have a sine cubed and a du. And the problem here is I can't change a sine cubed into cosines. So this is stuck. So remember when I started into this avenue, changing things to sines and cosines, I said, well, I have another tactic I'll use if this doesn't work. And that's always a good idea. Go into a problem with a couple tactics, because the first tactic just might not work. A u substitution is not going to be friendly here. You could try u equals sine, but you'd need to steal away a cosine, and you could do it actually. U equaling sine might work out for you, but I'm not going to do it here. Instead, I'm going to go to my second method. So I'm going to hit pause on this stuff because I'm just thinking that's probably not the best way to go. And instead, I'll go ahead and grab where we left off, the 1 over 6 to the fifth integral from 0 to pi over 4 of the tangent to the fourth of theta over secant of theta d theta. And I'm going to do what my second tactic, what I was thinking of, which is, tangent squared, which is kind of what we're looking at, can be traded out for a secant squared minus 1. So I'm going to go ahead and try that. Without doing any type of calculus, I'll go ahead and try some trig first. So this is a tangent squared squared. Hope you can be okay with me just saying that out loud. It's supposed to be a tangent squared being squared in there. But I'm going to trade out that tangent squared for its Pythagorean identity, which is a secant squared minus 1. It's a really kind of interesting tactic. Now I'm going to square that out, that numerator. And we get secant to the fourth of theta. This is going to be fun. Minus 2 secant squared of theta plus 1 all over the secant. It's actually not bad, although it does involve one of my favorite integrals. So let's go ahead and break that fraction apart. Notice I did trig before my calculus. Actually, I haven't done any calculus yet, except for my original substitution. That was a calculus move. The rest of it has just been trig. So I exchanged tangent squared for its trig identity. I then did some algebra by multiplying that out. Now I'm going to do some arithmetic by breaking apart this fraction. 0 to pi over 4. We have a secant cubed minus 2 secant plus 1 over secant, which is the cosine. Now, each of those you can actually integrate. So notice what happened here. I paused on something that should have been simple, sines and cosines, right? And then I traded out my work for something that looks terrible, but actually, when it comes down to it, each of these little sub-integrals here we can do. So let's start with the easiest of them. I'll leave a little space here. I'll leave 1 over 6 to the fifth out front. I'll leave some space here. The antiderivative of the cosine, I'll just write all the way over to the right-hand side. That's just the sine. And remember, we're evaluating these from 0 to pi over 4. All right. Minus 2. I'll put that right here. The antiderivative of the secant, that's the one that I told you guys are going to have to memorize. It's a very good one to memorize. The antiderivative of the secant is the natural log, absolute value, secant plus tangent. Technically plus c, but I'm just doing it within a problem. So this integral of the secant is going to be the natural log, absolute value, secant theta plus tangent theta. It's supposed to be a tangent. And then I moved from right to left here for a very specific reason. The integral of the secant cubed. I gave you a hint as to how to tackle the integral of secant cubed. The integral of secant cubed is 1/2 the derivative of the secant plus 1/2 the integral that's secant, which we just did over here. So plus 1/2 the natural log of the absolute value of secant plus tangent. It's a good way to remember that integral. And we are done integrating. Now we just have to evaluate. Before I evaluate, maybe I'll glue together those natural logs just really quickly. I hope you don't mind. I'm taking the time to do that. 1/2 secant tangent. Let's see, we have a 1/2 minus 2, so that's a -3/2. Natural log absolute value. And then finally plus sign. Evaluated from 0 to pi over 4. So let's go ahead and do this. All right. 1 over 6 to the 5th times the quantity. Okay. I was going to say something, but I won't say it. Pi over 4. So secant of pi over 4. Well, cosine of pi over 4 is 1 over root 2. So secant of pi over 4 is root 2 over 1. Tangent of pi over 4 is 1. Minus. Now I'm going to go ahead and take care of the natural log here. So -3/2. Natural log absolute value secant of pi over 4 is root 2. Plus the tangent of pi over 4 is 1. I don't need the absolute values on that because it's already positive. And then plus the sine of pi over 4 is 1 over root 2. Excuse me. Now, if I go back through and I try to plug in zeros, let's go ahead and do this. I'll do this in red, actually. Minus, so I'm starting to do all the subtractions here. Minus 1/2. Secant of 0, well, that's 1. Tangent of 0 is 0, though. So that goes. Plus 3/2. Natural log, absolute value. Secant of 0, again, is 1. Plus tangent of 0 is 0. And the natural log of 1 is 0. So that disappears as well. And then finally, minus the sine of 0, which we know is 0. So I'm just going to write a 0. All right. So basically, all the ink in red is zeroed out. And now you can, I'm going to factor 1/2 out of all of these. So that's 1 over 2 times 6 to the 5th times root 2 minus 3/2 natural log of root 2 plus 1 plus, I guess I shouldn't have factored off. Let's see, if you divide off 2, you get a root 2. There we go. Oh, well, that's kind of nice. So you could add up those 2 root 2s. Sorry about that. So let me go ahead and just put this together as 2 of these root 2s. There we go. All right. So, oh, and I don't need the halves. So that's a 3. Before anybody yells at me. Yeah. Oh, somebody already did. Okay. So there we go. That is the final answer. That's the area, as we often will forget, that's the area underneath this curve from 0 to 1/6. The area underneath this curve right here from 0 to 1/6. A lot of work involved in that problem. I'm going to mute while I take a sip. All right. So a good reminder of trig subs. Now, unless you have any questions, Or even if you have questions, you can type them in and I can hop back. But I'm going to hop forward to the next example here because we're starting to get into very obscure methods that are very powerful. This happens quite a bit. Integrate this bad boy right here. There are actually two ways to do this, but they both kind of lead to the same thing. Yeah, Avi, I'll go back. What do you need here? Just waiting, Avi. Oh, okay. All right. Okay, so going back to this guy. All right, so there are actually a couple ways to start this problem, but no matter what you do, you'll end up having to do what I'm going to teach you right now. So we might as well just go from the get-go with how I'm going to say you should approach this. If I take a look at this, I will often say do algebra before calculus. And in this case, the only algebra that you might be able to try to do is maybe factor this denominator. But I don't even think it factors, right? 7 is either 1 and 7 or 7 and 1. And let's see, it's 14 and 1 or 2 and 7. No, neither of those. So it's not factorable. I just did a quick little algebra check there. So no algebra can be performed here yet. Let me list out our tactics. I don't know the direct integral, so I'm not even going to bother with that. A u sub is considerable. Maybe we could do a u substitution. However, if you did a u sub, just quickly sketching it out, if you did a u sub here for this denominator, du would need to steal away a 4x minus 4. Now, some people will say, can you do that trick where I multiply top and bottom by 4? The answer is totally yes, you can. You can multiply top and bottom by 4, bring this 4 inside, and you have the 4x, and then you can say, well, I'll subtract 4 and then add 4. Great. Fine. But then this splits, just again, there are two steps to starting an integration problem. One is list out some tactics, like start thinking about things. And then two, think ahead. So this is part of me thinking ahead. If I did this u substitution, I would have something like, I don't need to be super exact. I just need to kind of framework it out. I have something like this plus something like this. Notice I'm not really being super exact here because the reality is, yes, I could do a u sub for this first one because if I let u equal the denominator, the du will steal away the numerator. Great. But I'm still left with 4 over the square root of that mess. So I still have the same exact issue I began with. So this doesn't get me anywhere other than it gets me half the problem, but I still have the lion's share of the problem left. So this is a little bit of foresight, looking ahead and saying, okay, well, no matter what I did with the u sub, I would still have to contend with that square root of 2x squared minus 4x minus 7 in the long run. So let's go ahead and not do a u sub here because it's just not going to be super helpful. But it's worthwhile to have investigated. What I'm showcasing to you what I showcased to you right there is that two-step process of listing out a tactic, and then looking ahead and trying to without doing too much work, trying to see, well, would that lead to a good method? The next thing we learned was by parts. But again, in this case, I don't think by parts is ideal. You can easily kind of see that this would be kind of a terrible problem. I'm not going to strike it out. I'm just going to say that it's probably not the best idea. It's definitely not the product. I'm going to write it that way. It's not the product of trig functions, so I'm not going to bother with that method. And it doesn't look like a trig sub will work here. However, this is our first example of a problem where you can force it to look like it needs a trig substitution. The way you do that is by completing the square in the denominator. So all that algebra that you learned way back when on factoring and completing the square, that stuff you learned back in your algebra days comes back to haunt you here. So let's go ahead and say this is equal to, and we're going to do algebra right now. I'm going to take that denominator, and instead of writing 2x squared minus 4x minus 7, I'm going to write 2 times the quantity x squared minus 2x, because that would give me minus 4x, and then minus 7. Okay, and then I have a dx off back. And that's just me starting the completing the square process. Now I will go ahead and complete the square, right? So x squared minus 2x plus 1. That would make this a perfect square trinomial. If it's been a while since you've completed a square, right, what you're doing here is you're taking half of this value and squaring it. So you take half of -2 and you square it. And that's what you're putting right here. Of course, you're adding something that wasn't there before. And so you have to offset that with subtracting that. Well, you're doing more than subtracting 1. You're subtracting 1 times this 2, because 2 is multiplying it. So I have to subtract 2 from the outside of that. Don't forget my dx there. And so this turns into the integral of x over the square root of 2 times the quantity x minus 1 squared minus 9. And that is now in a form where it is actually a difference of squares. It's the first thing squared minus the second thing squared. I can do a trig sub. So this is very common, incredibly common, in fact. So when you see a trinomial somewhere in your integral, and you can't do any other method, that's the key. Try to do anything else other than what I'm doing now. If nothing else will work, then complete the square. That's your only choice. So completing the square is very useful if you have a trinomial. But again, it's my personal last choice. It's not the first thing I would go for. So in this case, this picture sort of looks like a secant squared minus 1. I mean, obviously it's not, but it sort of looks like that. Veronica, why did I subtract 2 from the 7? It's because that 1 was not originally there. I actually added this 1 in, so I have to offset adding 1. However, if I subtract only 1 here, I'm not taking into account that 2 is multiplying that 1. So I actually added 2 when I added this 1 right here. I added 2 times 1. So I have to subtract off 2 times 1. That's why. Yeah. And let's see. So this is going to look like a secant squared minus 1, which is like a tangent squared. So I'm going to go ahead and I'll keep my green ink, let secant squared, actually I'll say let 2 times x minus 1 squared. Now watch how I do this. In reality, I need it to be a secant squared minus 1, right? So I'd like this picture, 2x minus 1 squared, to be a 9 secant squared. That would be the ideal situation. Because if it's a 9 secant squared, then, well, this would be a 9 secant squared. I could factor out the 9s, and I'd have a secant squared minus 1. It's a really cool way to do this problem. And then you take the square root of both sides, and you say, oh, that implies the square root of 2 times the quantity x minus 1 is equal to 3 times secant of theta. A really nice way to do that. And then you can take the differential of both sides. One thing you'll note here, by the way, I have this lonely little x in the numerator. So that's going to have to be traded out. So I might as well just solve this for x right now. I'll go ahead and divide both sides by root 2. And then I'll add 1. Again, it's because I saw that numerator has an x in it. So what are you going to do? You just have to isolate x. You're going to have to do it anyway. Might as well just do it right now. Now we take the differential of both sides to figure out what dx is. Well, that's 3 over root 2 times the derivative of the secant, which is secant tangent, d theta. Right? Derivative of 1 is 0, so we don't have to worry about that. So we have all the stuff we're trading out. I know exactly what x is. I know exactly what dx is. And I know exactly what 2 times the quantity x minus 1 squared is. So I'll make all of those substitutions right now. And I'll actually do that to the right here. This is equal to, I'll leave a little space because I know I'm going to be factoring possibly a number out. X is going to be 3 over root 2 secant of theta plus 1. That's what x is. Dx is a 3 over root 2. So that would be actually right here, but I'm going to move that out front, 3 over root 2 out front in this case. Let's see, secant tangent and then d theta. So secant of theta, tangent of theta, d theta. Be very careful here that secant tangent d theta is multiplying this entire statement in the numerator. So be very careful about that. And Avi, where did the -1 go from the secant squared of theta? The only secant squared I see is this one. And I don't know where a -1 would go. What do you mean it's -1? When it's secant squared minus 1. Oh, I haven't gotten to that yet. Right? So I'm not there yet. Yeah. So downstairs, we have a square root of 2 times the quantity x minus 1 squared. So square root of 2 times the quantity x minus 1 squared is 9 secant squared of theta. And then we have the -9. So all of our substitutions are made. Now we just have a lot of cleanup. So this is 3 over the square root of 2, integral of the quantity, I'll leave it like that, 3 over root 2 secant of theta plus 1. We have a secant of theta, tangent of theta, d theta. And that's all over. I'm going to take out the square root of 9 and park it out front. So obviously those 3's will cancel. And we'll have the square root of secant squared minus 1. But we know that secant squared minus 1 is the tangent squared. So that's the square root of tangent squared. Notice I'm trying to save some space here. And the square root of tangent squared, by our choice of theta, is going to be the tangent. And again, if you're wondering why it's not the absolute value, I have a video in our folder in 7.3 for that. But this allows us to cancel this tangent with that tangent. And so our integral becomes 1 over root 2 integral of, let's see, 3 over square root of 2 times the secant of theta plus 1 times the secant of theta d theta. The integral actually looked pretty terrible for a while there, but now you can see it's actually somewhat doable. Just distribute those that secant through, and you get 1 over root 2 times the integral 3 over root 2 secant squared. We know the antiderivative of secant squared plus secant of theta, and we happen to know the antiderivative of secant of theta. And so this will be 3 halves tangent, because that's the antiderivative of the secant squared, plus 1 over root 2. Antiderivative of the secant is the natural log absolute value of secant of theta plus tangent of theta, and absolute value plus c. Now, probably the biggest mistake that'll be made is leaving it like this, because we did not start in the world of theta. We started in the world of x. So we're going to have to figure out what theta is in terms of x, or how they're related to each other. Zooming into all of our work here, you'll note that at this point right here, that's where we initially made our basic link between theta and x. So this tells us that root 2 times x minus 1 over 3 is the same thing as the secant of theta, which, by the way, I don't need to draw a triangle for that, because well, I mean, I do, but at least for this secant down here, I can trade it out immediately for a root 2 times x minus 1 over 3. But I do have to draw a triangle to figure out what the tangent is. So let's go ahead and draw a right triangle. I always draw them as if they're in quadrant 1, even though they don't have to be. Here's theta. The secant is hypotenuse over adjacent. Hypotenuse, therefore, must be root 2 times x minus 1. That's supposed to be a 1. And adjacent must therefore be 3. Now you would use the Pythagorean theorem to figure out what this missing side is. You would have this hypotenuse squared minus this 3 squared. And believe it or not, that would become the square root of whatever we had. Where is it? 2x squared minus 4x minus 7. If you just multiply it out, it will work that way. So I'll leave it to you. But let's go ahead and just plug in all the information. So we have 3 halves times the tangent. Tangent is going to be that square root of 2x squared minus 4x minus 7 over 3. So it's going to be 1 half square root of 2x squared minus 4x minus 7 plus 1 over root 2 times the natural log absolute value of the secant. Secant was root 2 x minus 1 over 3. Oops, over 3. Plus the tangent, and the tangent is that square root business all over 3. And then finally, plus c. There is a little bit of there's a little mathematics you can do here. Obviously, those fractions here could be combined if you want to. You don't have to. Also, if you were to see this, let's say in a handwritten solutions manual or something like that, the likelihood is that somebody's going to write this as follows. You don't have to. So maybe I should write this maybe in blue just to say this is an optional way of writing this answer. 1 half square root of 2 times the quantity x minus 1 and quantity squared minus 9 plus natural log of, sorry, it should be plus and a 1 over root 2. Natural log of, just seeing if that has to have, it does have to have the absolute value. Root 2 times x minus 1 plus square root of 2 times x minus 1, quantity squared minus 9, and absolute value plus c. You will often see it written that way, and you might think, wait, hold on a second, there was division by 3. Well, there it was, right? But remember, you have this natural log of some mess over 3. That's the same thing as natural log of that mess minus the natural log of 3. And that is just a constant, so it gets folded into that. So that's why you might see it written different ways. They're both the same. They're both correct. They'll both be marked correct. So if somebody posts something on the forums and they say, well, I got this answer, you might look at it and go, oh my gosh, my answer doesn't look anything like that. But actually, if you think about constants being folded into that C and some maybe logarithmic manipulations, they probably are the same. Okay. A pretty robust problem, but that idea of completing the square to get to a solution is very, very popular. So we do have to do that, despite nobody loving completing the square. I'm going to mute for a drink. Notice, by the way, when I started the problem, I listed out tactics and I really tried to save that trig sub, the completing the square, for the very last one. It was purposeful because I don't like to use completing the square if I don't have to. There's too many algebraic mistakes that can occur. So always look elsewhere. In fact, I'm just putting together a tactic guide that I'll put out later on today, possibly. And you'll see that actually the way I'm writing the tactics, I'm writing it the way we've learned them. But in reality, the way that I approach the tactics is somewhat different. By parts, in fact, is usually my last tactic. I generally don't like to use by parts if I can avoid it. It's very powerful, don't get me wrong, but it's also lengthy if you have to use it. So I generally save that to the end. All right. I sometimes give myself a hint in my example instructions, a case for symmetry. So it's obviously this does not look symmetric. So you can ignore that statement initially. But if you take a look at this, a simple, harmless looking integrand, right? Square root of x minus x squared. It doesn't look like it's super dangerous, but a u sub will not work here. By parts will not work here. It's not the product of trig functions. It really is just the only way you can really approach this is the way we did it in the last example, which is completing the square and then a trig sub. So I will just make that mention here. Complete the square plus trig sub. CTS means complete the square. So we're going to complete the square and then do a trig substitution here. And when I do a completing the square, I've always been, you can probably tell via lecture, I've always been kind of long-winded with things. So I do take my time. I'm going to write it this way, negative x squared plus x dx. I just like it that way, like to write it that way. And then I'll go ahead and factor out the negative. Not out of the radical, you can't do that, but at least I can factor the negative out of this. I get x squared minus x. And then I'll leave a little space here, dx. Right now, the way I've written it, I haven't changed anything. However, now I'm going to go ahead and complete the square. I'll take 1/2 of that, and I will square it. Okay, that's not, when I write that, I'm not saying take 1/4. I'm saying taking 1/2 of that -1, and I'm going to square it. Maybe I should just say plus square. So 1/2 of -1 is, well, -1/2, and you're going to square it. Okay, so I'll say -1/2, and then I'll square it. It actually does become a -1/2 in a square. All right, now, when I take a -1/2 and square it, obviously it becomes a positive 1/4. But remember, you're going to be multiplying that by a negative. So really what I've done in this problem is I've subtracted 1/4 from the inside of this. So I need to add back 1/4. Okay, that's completing the square. And now I'm going to choose to write it in a different order. I'm going to write this as, well, maybe I'll take my time. Minus, I have that negative sign, then this is going to factor to x minus 1/2 and quantity squared. And then we still have that plus 1/4 and a dx. And now what I'm going to do is reverse the order because I dislike having the subtraction go first. So I'm going to write it this way. 1/4 minus x minus 1/2 n quantity squared. I just think that's a better way to do it because then you can see what substitution you're going to make. This is definitely going to be a trig substitution because it's a difference of squares in there. So the difference of squares tells me that I'd like to make, or I'd like to let, this picture be the sign. So it's like a 1 minus sine squared, right? That's what I'd really love for this to be, a 1 minus sine squared. So I'm going to go ahead and let the quantity x minus 1/2 squared be sort of like a sine squared, but I don't want it to just be a sine squared because I don't know what 1/4 minus sine squared is. So I'm going to tack on a 1/4 to the coefficient. So 1/4 minus 1/4 sine squared. I can factor out the fourth, and I have 1 minus sine squared. That's a cosine squared. Take the square root of both sides so you can figure out what the initial sub really was. And then you can find the differential of both sides here. dx will equal a 1/2 cosine of x, or sorry, cosine of theta, d theta. And I will also change the limits of integration while I'm at it. So x equals 0 implies, well, let's see, where's my relationship? If x were 0, that implies negative 1/2 is equal to 1/2 sine of theta. Well, that means that sine of theta is equal to negative 1. Sorry, I was just thinking of something. Sine of theta is equal to negative 1. And I'll even write that in. Negative 1 is equal to sine of theta, which means theta is equal to negative pi over 2. And then the upper limit being 1, again, substituting that into here, 1 minus 1/2, we get that half should equal 1/2 sine of theta, which implies 1 is equal to sine of theta, which implies pi over 2 is equal to theta. So let's see, what have I been able to substitute out? The limits, I now know what those are. Let's see, the x minus 1/2. Let's go ahead and highlight that, squared. I know what that is. And the dx. The dx is right here. So those are my things I'm going to substitute in. I'll go ahead and just do it to the right here. So our integral becomes the integral from theta equals negative pi over 2 to positive pi over 2. And right when I write that down, negative pi over 2 to positive pi over 2, I immediately, it's like my spidey senses go off, and I immediately know that a symmetry might, the case for symmetry might be usable. In other words, I might be able to use the fact that we're integrating over a symmetric interval. Let's see, we also have the square root of 1/4 minus, and then that kind of pinkish mauve color highlighter turns into 1/4 sine squared. And then dx turns into 1/2, which I'll pull that out front, cosine of theta d theta. And that integral is really what we're going to be dealing with for the rest of the problem. We don't have to trade back into the world of x's. This is a definite integral, and we have completely transformed its value or its variables into the world of thetas. So we do not have to transform back into the world of x's from this point forward. I'm going to factor out a 1/4 out of this square root. So square root of 1/4 is a half. I'll pull that out. Half times a half is a 1/4. Negative pi over 2 to a positive pi over 2. And we'll be left with square root of 1 minus sine squared, which is the square root of the cosine squared. And we know the square root of cosine squared is going to be a cosine. And so if that's a cosine times a cosine, that's going to be a cosine squared. All right. So there are 3 ways you can integrate this. Actually, are there 3 ways? Yeah, there are actually 3 ways to integrate this. One, you could just use it, the cosine squared right here. Well, actually, it's 2 ways. No matter what, if you left it with cosine squareds, which is probably what most people are going to do, if you leave it as cosine squared, you'll have to use a half angle identity. I hope everybody's okay with that. You know what a half angle identity is, all that fun stuff. So you could totally do that. The other way is to trade it out for sines by writing it as 1 minus sine squared. But the fact is, even if you trade it out for sines as a 1 minus sine squared, you have a half angle identity. So no matter what, you're going to have to use a half angle identity here. So I'm just going to trade out this cosine squared for its half angle identity, or the power reduction formula, however you want to say that. I haven't run the integral yet, but each time that I'm writing it, I'm thinking of the fact that I'm integrating over a symmetric interval. And so I'm really hoping that every step of the way, I continually look and think to myself, is there something I can take advantage of? For example, in this case, I know the cosine squared looks something like this, from negative pi over 2 to positive pi over 2. So I could technically integrate from 0 to pi over 2. Totally could. And I still might do that, by the way. But for right now, since I haven't run the integral yet, I'll go ahead and just continue my manipulation. So I'll pull out that half from the denominator. So I get a 1/8 integral from negative pi over 2 to positive pi over 2 of 1 plus the cosine of the double angle. Those power reduction formulas end up coming into play quite a bit. All right, let's talk geometry. First of all, if this is the x-axis, this is the y-axis, this function y equals 1, well, that's just a graph of height 1, and we're integrating that, or finding the area underneath that, from negative pi over 2 to positive pi over 2. That is a distance of pi with a height of 1. So the area is pi times 1, or pi. So again, that's 1/8 pi. Notice how I'm just trying to hammer in a little bit of geometry for you guys, because it's great to let go of the mechanics every once in a while and think geometrically. It allows you to compute without needing to integrate. The next part there is the cosine of the double angle. That just means you have a cosine curve that's going twice as fast as it normally does. That is, whoops, that's the sine. Normally, if I had half the cosine curve, which I have right here, okay, let's just talk about the full cosine curve. Normally, the full cosine curve does its complete circuit from 0 to 2 pi. I think everybody would agree with that. So it does half its circuit from 0 to pi. Again, I think everybody would agree with that. However, we're not dealing with the cosine. We're dealing with the cosine of the double angle. And so it goes twice as fast. That is, it does a full circuit in time pi. It goes through half its circuit in time pi over 2. This is the cosine of the double angle. And we're integrating that from negative pi over 2 to positive pi over 2. That is going to be 0, because the areas cancel. This is area A. This is the same area. This is the opposite area. This is the opposite area. They cancel beautifully. I highly recommend you get used to thinking geometrically so that you don't have to do the mechanical integrations. You can just say, oh, this is just pi over 8. Because that is going to be 0. Again, it's the cosine curve. It's going twice as fast. So from 0 to pi over 2, it goes through half of its regular circuit. from 0 to pi over 2. Well, we're integrating from negative pi over 2 all the way up to that positive pi over 2, and those areas will cancel each other out. It's a really beautiful method. So again, that's why I reminded myself at the beginning, a case for symmetry. You want to take advantage of symmetry as often as possible. I haven't snuck in enough examples. I like to do that so that it keeps you fresh. It keeps your mind sharp as you're going through these problems. There should be possibly questions on something like that. So I'll take a drink while people type in questions. Okay. If you do have questions, I'll keep looking up in the chat. But really cool, beautiful way of dealing with that problem. And then this is the one I did in a video, so I'm not going to do that here. So we are done with section 7.3. And like I said, the last example I just did in a video because it's actually, you can see it right here. I did this, and I highly recommend you watch the video. I did this using a trig sub because it has that difference of squares in there. But then at the end of it, I said, what if we did a U sub? And you can see the U sub is actually really clean, very beautiful method. So highly recommend you watch it. It covers both tactics. So very, very cool.